In this unit, we're going to discuss similar figures. So to start off, we're going to talk about a similarity transformation called a dilation. So a dilation is a transformation that produces an image that's the same shape but a different size. So a dilation is not a rigid motion. So let's just add that. So it's not a rigid motion. Because if you remember what a rigid motion is, it's a transformation that preserves angle measures and side lengths, also meaning it preserves shape and size. But for a dilation, the size is going to be different, meaning the side lengths will change. So the angle measures will stay the same, so I'm going to write that above it, same angle measures. That's what's keeping the shape, but different size. So different side lengths. So dilations create what we call similar figures. So in this unit, we're going to be discussing similarity. So we start off with talking about dilations because that's how we produce similar figures, meaning the sides will be different, but the angle measures will stay the same. So it's not a rigid motion. It's actually called a similarity transformation. So called a similarity transformation, meaning it produces similar figures, not congruent figures. So let me just underline that, similarity transformation. So when we talk about dilations, kind of like when we talked about rotations, translations, and reflections, there's different things you need to include when you're talking about them. So for a dilation, you have to include the scale factor. So that's how big or how small your object is going to become. So that's the ratio. And then the center of dilation. So the center of dilation is where all of the points are either expanded from or contracted to. So the center of dilation is a fixed point, meaning it's going to stay in the same position. So it's going to remain invariant. It's the only point that remains invariant. And remember, invariant means remains the same. So if you think about what's happening, if we look down in these examples, the center, so this is the center of dilation. This is the center as well. That point you have to imagine is getting locked in place, meaning it's fixed, stays in the same spot, and everything is getting measured from that point. So if you look at triangle ABC, that's the original, and then it became triangle A prime, B prime, C prime. You can see that everything is getting expanded from that center point. So the measurement we use is always from that center. So when we talk about a dilation, so if we look at this example, we're going to identify the dilation and find its scale factor. When we talk about a dilation, the notation we use for a dilation, capital D is going to be the symbol. Makes perfect sense for dilation. So capital D. And then you need to specify those two things. So the center and then the scale factor. So that's the notation when we're describing a dilation. Now you can write it out and say a dilation centered at point O with a scale factor of, or you can use this symbolic notation. So let's go ahead and look at these and be able to use this notation to describe what's happening in the picture. So we already talked about the center. So we know that the dilation, so it's a dilation that occurred because the image is much larger than the pre-image. So it's an enlargement. The center is O. Now we have to find the scale factor. So the scale factor requires a little bit more thought, and that's going to be using those distances. So notice that the sides are not labeled, but these distances are labeled from the center. So what happens is when you do a dilation, you use the center and you go to each pre-image and then image point using that scale factor and using the scale factor to multiply by your original distance. That's how you're going to get the new distance. And what that does is it forces the side lengths to be in that same ratio as those distances. So to find the scale factor off to the side here, there's kind of a formula you can think of. So what happens is you take the old distance from the center, you multiply that by the scale factor, which typically we use K as the scale factor. It doesn't really matter, it's just a variable we use, and that's going to equal the new distance that you travel to do the dilation. So what that means, if I look, the old distance is from the center to the original triangle was 2. So I'm just going to do this down here. So for the scale factor part, the old distance was 2. I multiplied that by whatever the scale factor is, which is what I'm trying to find, to get this new distance from the center. It's always going back from the center to C prime. So that new distance was 6 units. So the original distance times the scale factor had to give me 6. So you could really just see that 2 times 3 is going to give me 6, but sometimes the numbers aren't as easy to see. So you can just solve this equation, and that's going to give you your scale factor. So my scale factor is 3. So that means the pre-image compared to the image, the smaller triangle is 1/3 of the bigger triangle, or the big triangle is 3 times that of the smaller triangle. So though all of the corresponding sides will be in that same ratio. It's just when you do the dilation, you use the distance from the center because everything's getting expanded or contracted from that center. So here's your notation for the dilation. So it's dilation centered at O with a scale factor of 3. So you can write it out or use a symbolic form. So let's go ahead and try the next one. For this one, we see that segments are being dilated. So it's not a full triangle. So remember, these dotted lines are representing that distance from the center, not part of the actual shape. So in this case, we're starting with the non-primes. So this is the pre-image. Here's the image. You can see it got smaller. So smaller meaning it should have a scale factor that's less than 1. So when it's on an enlargement, you have a scale factor greater than 1. In this case, we're reducing. So essentially, you're dividing that distance. So if we go ahead, we know that the dilation will be centered at O. And then to find our scale factor, the old distance from the center to the original was 5 units. So the old distance was 5. We had to multiply that by the scale factor to get the new distance. And the new distance is 2 to get to C prime. So we go ahead, we divide that. And in this case, we see that the scale factor is 2/5. So again, a fraction because you're really making this smaller. So you should be multiplying by a fraction. So my scale factor is going to be 2/5. And notice I didn't have any negative numbers here. So when you do a reduction, that means you're going to have a fraction. So 0, your numbers have to be between 0 and 1 for a reduction, and greater than 1 if you're doing an enlargement. Because if you have a scale factor of 1, the figures aren't going to change because you're just multiplying the distances by 1, which means everything stays the same. If you see negative, that deals with direction here, and we'll talk a little bit more about that in class. So looking at these examples here, now we're going to actually do some dilations by using a compass and a straight edge. So we're going to do these in plane space, and then eventually we'll look at them in the coordinate plane. So go ahead and grab your compass and your straight edge, and we're going to basically apply the same concepts that we talked about up top. It's just we're going to be doing them the opposite direction. So the first thing you have to look at is this notation. So this is saying to do a dilation, my center is O, and the scale factor is 2. So this really means you're going to double your distance. From the center. And that from the center is always going to be so important. Remember, we're always talking about that center point. So, and then it says of segment AB. So that means that's what you're going to do the dilation to. So the first thing you need to do is we need to draw in those dotted lines. We need to have, because if you think about what happened up top, the image point was always on the same line or collinear with the center and A. So we need to go ahead and have those lines in there so that we have a starting place, so that we know where our point's supposed to lie. So let's go ahead and we're just going to sketch dotted lines so that you know it's not really part of the final image, but it is an important part of the picture. So go ahead and, oops, let me grab my segment tool. So use your straight edge to do this. So go ahead, and it doesn't really matter how long you make them. If they end up being too short, well, then all that means is you're going to have to extend them. So I'm just going to go ahead and draw those dotted lines. I know that A prime has to be somewhere on this line segment and B prime has to be somewhere on this line segment. So now what I need to do is I need to start at the center and I need to measure that distance from the center to A. I need to measure that old distance. So I'm going to go ahead, I'm measuring the old distance. So I'm going to go mark an arc there representing that I really did measure it. So I made this dotted. So measuring that old distance. And now we need to double that distance from the center. So from the center, here's that distance once, I need to double it. So that means I really need one more of those. So that total, this distance is doubled. So from O to A prime, which is going to be right here, that distance is twice the distance of OA. So then we repeat that process. So we're going to go ahead, take your compass, place it on O, measure to point B, and there's the original distance. We'll multiply that by 2, so that means you need one more of those so that the total distance from O to B prime is twice that of OB. So there's B prime, and then I go ahead and take my straight edge and connect them. So A prime to B prime, and that's it. There's your new segment. And you should see that these end up being parallel, and we'll talk more about those properties, but dilations will preserve parallelism, so these lines will end up being parallel. So moving on to the next one, and the last one here, we are going to shrink this. So again, let's start off by drawing our lines, our dotted lines, because we know that our end results, our image points, will all lie on the same line as the pre-image points in the center. So I'm going to go O to B, O to D, and O to A. And now for this one, my center I already started with, but notice that I have a scale factor of 1/2. So this means that you have to, the distances from the center have to be half as far. So you're going to take half, let me rewrite this, take half the distance from the center. So what you need to do is, if you think about measuring from O to A, well, now you need to do half of that. So in order to do half the distance from O to A, the only construction that we know to be able to find the middle of this is to use the perpendicular bisector construction. So from O to A, let's start with that. We're going to take our compass and we're going to go more than halfway and use the perpendicular bisector construction. So this construction, you can see, comes up all the time. It just keeps coming up. So we're going to go more than halfway, keeping those arcs the same, using my endpoints O and A. And then I'm going to take my straight edge and I'm going to make it the same color. I'm going to connect these. And that midpoint right here is going to be A prime, because now this is a reduction. I went half that distance. And we're going to repeat this process for the other 2 points. So let's go ahead, take our compass. I'm going to go ahead and use O and D this time. as my endpoints. So using highlighters here can be helpful to color code so you keep things organized as you're doing them. So I'm going to mark my arc, making sure that it's going to actually connect. Do the same thing from point D. Take my straight edge. I'm going to keep everything in the same color. And that's how I found the midpoint of segment OD, meaning this has to be D prime. This is halfway. And then lastly, do the same thing from O to B. So start at O, go more than halfway, go to B. Looks like this one I might have to go back to my original arc and extend it because I don't see the intersection. And again, color coding this is so helpful so that you're looking at the correct intersection, because if it's all in pencil, it's very easy to mark the wrong intersections when you draw your line segment. So you don't have to necessarily change out the pencil in your compass, but you could just highlight over your arcs. That way you can keep track of them. So then this point here, or this point of intersection of the green segment and OB, that's the midpoint. So that's going to be B prime. And then the last thing is just to make my triangle. So the triangle is going to be connecting. I'm not going to use that segment. It's going to be connecting A prime, B prime, and D prime. And your triangle should look like half the size of the original, and it should look like that the segments that correspond are parallel, and the new segment should be half the length of the original. So there you have it. The most important thing though is that we're always going back to that center point, and that distance is what changes when you multiply by the scale factor. So go ahead and fill out your key ideas from this lesson and complete the check your understanding problems, and we'll discuss those tomorrow in class.